Randy Leveque. He's now Emeritus Professor of Applied Mathematics at the University of Washington, where he additionally holds positions as Adjunct Professor Emeritus of Mathematics and Earth and Space Sciences, and is also a Senior Data Science Fellow at the eScience Institute. Randy has co-authored 5 books, one I'm currently using for my numerical PDE course, but he has a recent one on Riemann problems and Jupyter solutions that was just published by SIAM this year. Randy is a fellow of SIAM and also a fellow of the AMS, that's the American Mathematical Society. We all have really Randy to thank for being here today, as he was the founding organizer of this meeting, the Pacific Northwest Numerical Analysis Seminar back in 1987. So today, Randy will tell us about efficient probabilistic tsunami hazard assessments using clustering and multi-resolution modeling.
Well, thank you, and thanks for the invitation to speak. I always enjoy being part of this seminar. And thanks to the organizers for keeping this going, especially in this trying time this year. And also for updating and taking over the web pages. I think Thomas did a lot of that work, but it's great that my 1995 web page has finally been replaced by something a little more modern, and also for pulling together all the history. There was a lot of missing history of past meetings, but if you go to that website now, you'll find lots of the old schedules, and it's kind of fun to look through the history. Okay, so what I'd like to talk about today is some work we've been doing recently on probabilistic tsunami hazard assessment using clustering and multi-resolution modeling. This is really kind of an interdisciplinary project, so this can be also a very much application-oriented talk. My co-authors, Amy Williamson, is now at the National Tsunami Warning Center in Alaska, but until recently she was a postdoc working with Diego Melgar at the University of Oregon. Diego's a seismologist by training, but he's been doing a lot of tsunami simulation as well and used our software quite a bit, so we've been working with him for several years now. Don Sabrim, a former student, is now at the Kron Institute, and Lois Adams and Frank Gonzalez here at UW, who I've been working with a lot in the last few years on tsunami modeling, in particular for Washington State coastlines, and some of the projects I'll mention briefly as we go along. Let's see if my slides are working here. So yeah, so the most recent work is in this preprint that should soon appear in Frontiers in Earth Sciences. But this is building on some work that we've been doing earlier as part of a FEMA project on how do you do probabilistic hazard assessment for flooding due to tsunamis. FEMA has always looked sort of flood inundation maps from other kinds of flooding, 100-year floods for precipitation events and things like that. And we're interested in how to extend some of that to tsunami modeling. But there's a lot of interest now in Washington State and elsewhere in doing probabilistic modeling, as I'll talk about a bit later. So Donna already introduced a lot of the background about tsunamis. Thank you, Donna. But what we'll be looking at mostly are the big subduction zone earthquake tsunamis, when you have the subducting oceanic plate subducting beneath the continents, and it sticks for hundreds of years perhaps and deforms the plates, and then every now and then there's a huge release of all that energy where the plates move substantially, and since much of it's under the water, it typically lifts up a large hump of water that propagates as a tsunami. And the results of that can be devastating, as we saw, for example, in 2011 in Japan. So here on the West Coast, the Pacific Northwest, we have this Cascadia subduction zone that we have to worry about, which actually until the 80s or so, it wasn't known that it was even active, but now it's known that there are magnitude 8 or 9 events on this subduction zone, on average every 500 years over the past 10,000 years based on geological evidence, but it's a lot of variation in how long it is between events, and the last event was known to have happened on January 26, 1700, so a little more than 300 years. So it could be any day that we're due for another one of these. So there's a lot of concern on the West Coast and Washington State in particular on how do we better prepare for potential tsunamis. In the shallow water equations, which Donna introduced, we're looking at two-dimensional simulations. So the variables are the depth and 2 horizontal momentum components. We have terms that come from the hydrostatic pressure, as well as the bathymetry on the right-hand side. The gradient of the bathymetry comes in as a source term. As Donna mentioned, in many cases, you need to add dispersive equations to properly capture the waves. But for the very long wavelength tsunamis that are created by these subduction zone events, the shallow water equations are generally adequate for the kinds of things that we want to model and have been validated to work quite well. Adding in the dispersive terms, as Donna mentioned, it makes it much more complicated, especially in the context of adaptive refinement. She mentioned the boost claw code that my former student Yuan Kim had worked on. That didn't include adaptive refinement, however. Marcia Berger and I are now working on a project to try to incorporate dispersive terms into GeoClaw with the adaptive mesh refinement, but that's an ongoing project. That's something funded by NASA for looking at asteroid impact tsunamis, where we have much shorter wavelengths in the tsunamis. Also, landslide generated tsunamis can give rise to much more dispersive phenomena. But today, well, I'll focus only on the shallow water case, in which case we can use the GeoClaw software that's been pretty extensively developed starting about 15 years ago now, based on the ClawPack software before that, which uses adaptive mesh refinement and OpenMP. It's all openly developed on GitHub, so you're welcome to take a look there. Many people have been involved in this. Marcia from the beginning on the adaptive mesh refinement. Dave George was the one who started the tsunami modeling part of it. Tal, Donna, and others. We have a web page that lists many of the projects that we've been doing here at the University of Washington recently. And I just wanted to show one animation from that page, if this works, which is a sort of a simulation of a major magnitude 9 type earthquake happening on the West Coast and propagating into the Strait of Juan de Fuca here. This is Washington State here, Puget Sound over here, Seattle is right down here. So you can see it takes a couple of hours for the tsunami to reach Seattle, for example. On the other hand, on the outer coast, it arrives within a few minutes. And then you also have these edge waves that can propagate up and down the coast for many hours after the event. So trying to model exactly what happens from any specific hypothetical earthquake is already a big computational problem. And now what we'd like to do is extend that to sort of probabilistic analysis. Okay, so here's Washington State again. We have something like 3,000 miles of coastline in Washington State, so there's a lot of modeling to be done. But today I'm going to focus on this one little area down here, Grays Harbor, west of Aberdeen, and these two peninsulas, Ocean Shores and Westport, at the entrance of Grays Harbor, which are very low-lying, basically sandbars, but they're quite heavily built up now. This one's about 10 miles long, this one about 5 miles long. And what happens in the aftermath of one of these large tsunamis is that these peninsulas can be almost entirely overrun in the worst case. So this area down here in Westport, Washington, is what we've zoomed in on here. And what's shown here is sort of the maximum flooding depth for this one particular event that's been studied here, which shows that there's this one little ridge of high ground that doesn't get wet, but pretty much the rest of the peninsula does. And what we see down at the bottom is a cross-section, a transect cutting through the middle here. And these buildings that you see here are actually a set of school buildings, and Ocosta Elementary School is important here because that's the site of the first vertical evacuation structure that's been built in North America. Because there's not time to evacuate from this peninsula during a large tsunami, instead they built a new school there that has a tsunami safe area on the roof. And so this is something that we were involved in doing some of the tsunami modeling for the design of back in around 2012-13. It's since been built. This is a picture I took this summer up on that roof, which can hold, it's designed to hold 1,000 people. It could hold 2,000 in a pinch. We were there flying drones and collecting some LiDAR data to do more detailed three-dimensional modeling of the area around the school and some of the other critical infrastructure around Westport. But we've worked quite a bit with people in the Westport area, and so that's one of the communities that we focused on for this particular probabilistic study. So The other thing we've been doing a lot of recently is mapping different areas along the coast for the hazard maps the state of Washington publishes. This particular one actually was done by the NOAA Center for Tsunami Research. We've been collaborating with them. They've been doing parts of the coast. We've been doing other parts. So the Westport area they did, but they get very similar results for this same event that we were modeling, where there's a bit of dry land here and most of the peninsula is flooded. The problem with this sort of map is this particular event that's been modeled here is what's thought to be not the average Cascadia earthquake, but something like a 2,500 year event, one that's less probable than the next one that's probably coming our way. And so this may give an overly pessimistic view of how bad it could be and could be misleading in terms of getting people to prepare properly for a smaller event that would be much more survivable if they know the right thing to do. So that's one reason why there's a lot of interest now in doing more probabilistic studies, where rather than modeling a single hypothetical earthquake, you want to look at a whole range of earthquakes and see what range of flooding depths are possible, and then try to assign annual probabilities to different flooding depths. So the idea in the probabilistic tsunami hazard assessment is to first create what's called a hazard curve at many points over a community from which you can make maps. And so a hazard curve is a function that tells us for a given flooding depth, for example, so H hat will be some exceedance value, in this case, say depth of flooding. It could also be a speed of flow if you're interested in maritime hazards out in channels, for example. But onshore, it's typically the depth of flooding that we're looking at first. And so what you would like to know is what's the probability that the depth is going to be greater than that. And you want to calculate that for lots of different values of H hat, and then you can plot that probability as a function of H hat, and that gives us a hazard curve at one particular spatial location. And then from that, you could also invert and say for a given annual probability, like 1 over 500, if you're looking at a 500-year event, or 1 over 2,500, what's the depth that you might expect, what depth of flooding might you expect with that probability? So once we have a hazard curve at each point, we can calculate some of these quantities that are useful for doing probabilistic hazard assessment. The 2,500-year time frame is useful because these vertical evacuation structures, for example, have to be built according to a certain code that says you have to do tsunami modeling relevant for a 2,500-year event in designing that kind of structure. So to do this, we first of all have to come up with sort of an overall annual probability that some tsunami-genic earthquake is going to happen. What's the probability each year that we'll have a tsunami? So of course, earthquakes can be small or large, and this moment magnitude is often used as a measure of the energy in the earthquake. And typically, if the magnitude is 7.5 or greater, then you might expect a possible tsunami. And so we could try to assign some probability to that. And then a brute force Monte Carlo method would be to suppose we have not just an overall probability, but we actually have a probability density of all the possible tsunami-genic earthquakes that could possibly happen, and just choose some very large number of samples from that density, and then do a fine-scale tsunami simulation for each of them, and then record the maximum depth from each of those simulations at each point of interest covering your community, and then look at, as an estimate of the annual probability of exceedance, look at how many of those random samples gave you exceedance of the particular value H hat at this particular point. So if out of these n random samples, n hat is the number that gave a maximum flooding depth greater than H hat, then we could estimate the probability that H is greater than H hat by the fraction of the simulations that gave that amount of flooding times the overall probability. So the one problem with this, well, there's several problems with this. One is we have to define this probability density of all possible earthquakes, but also even if we had that exact probability density and we decide to look at all magnitude 7.5 or above, the ones that are 7.5 are unlikely to produce much of a tsunami. On the other hand, they're much more likely to happen than the larger ones. And there's this Gutenberg-Richter law that's kind of a rule of thumb, at least, on how likely earthquakes are of different magnitudes, which says that for different magnitude events, the probability decays exponentially with the magnitude, and in such a way that a magnitude 8 event is roughly 10 times more likely than a magnitude 9, and a magnitude 7.5 event is 32 times more likely than a magnitude 9. So if we just sampled a large number of realizations from the correct probability density, assuming we knew that, then we'd get probably 32 or so 7.5 events for every magnitude 9, and we'd be doing lots of tsunami simulations of events that have hardly any flooding at all. So one way to avoid this problem is relatively simple application of the idea of importance sampling, that we want to sample the less likely but more serious events much more densely, but then weight them with a smaller weight when we calculate the total overall probability from those. So the way we've done that in this particular study was to break our tsunamis up into 4 magnitude classes. You could have many more, but we chose 4, 7.5, 8, 8.5, and 9, and assign a probability to each. So of course, the probability for the 9.0s would be smaller than for the other ones. But then you can take as many samples as you want from each of the classes, and in particular, you can take lots of magnitude 9 samples, and then as your overall probability, look at how many flooded from class J, call that n hat J out of n hat, and then weight that by the probability of that class when you calculate an approximate probability overall. So you can think of each event as being assigned sort of a weight that's the probability of that class divided by the number of samples you're going to take from that class. And then after doing each tsunami simulation, you just add in that weight for each of the events that exceeded the value H hat that you're looking at. And you do that for lots of different H hat values. So that still begs the question, though, how do we come up with, even within one of these classes, how do we come up with a probability density of earthquakes of that size that we can sample many times over and get something that's geophysically reasonable? This is one of our standard geoclaw examples of a tsunami that was generated off the coast of Chile in 2010, just to show you sort of what the adaptive mesh refinement of that tsunami as it propagates outward is. But what I want to focus on now is what was happening right here on the coast of Chile. There's a zoom of the coast of Chile that initiated that tsunami. So what happened is that there was some seafloor deformation, which is shown here in the red and the blue, which was lifting up the water, and often the coast itself subsides, which is also a problem in tsunami modeling that can increase the flooding. But because of the way that the subduction zone is oriented, that's often the pattern you see on the seafloor. But this is generated from some assumption of how the slip was distributed on the fault surface, the interface between the subducting oceanic plate and the continental plate. So this is several kilometers down in the earth. And the geometry of the fault is pretty well known, but the slip distribution on that fault can vary dramatically from one earthquake to another. So this particular slip pattern that's shown on the left here that generated the seafloor deformation is the kind of thing that can be recreated by solving inverse problems by the seismologists after an event happens, by taking all of the seismic data that's been collected at many different seismic stations, and from those inverting to see what the slip was that created the earthquake. And then for tsunami modeling, we can also take that slip and translate it into seafloor deformation. I won't say too much about that, but there's a simple sort of Green's function model called the Ocosta model that assumes an elastic half space that lets you take slip on patches and convert it into the resulting deformation of the surface. That's typically accurate enough for the kind of tsunami modeling we do. So if we want to generate random earthquakes, what we want to do is come up with random patterns of slip and use those to generate seafloor deformations, and then put those into our tsunami model. So you could think of a random earthquake as being simply a random slip pattern on however many fault segments you have. So in this picture, I think there were 180 little subfaults here. And so this would be a vector of length 180. and then you could try to choose random values of all of those. Of course, you don't want to just put down a uniform grid in a 180 dimensional space and sample it. But we also know that the slip on these different subfaults is not going to be uncorrelated. If you look back at this figure, even though it's kind of patchy and it's much larger some places than others, it's also somewhat smoothly varying. And there's a sort of a typical correlation length that can be estimated from this kind of inversion of lots of past earthquakes. And so we know that we have some correlation, that if we look at the slip on the ith subfault and the jth subfault, that the expected value of SI minus its mean times SJ minus its mean is some covariance matrix that we can estimate a priori. And so then the question becomes, how do we generate random samples that have a reasonable correlation matrix, or covariance matrix? And for this, we use the Karhunen-Loève expansion, which Hongkai Zhao mentioned briefly this morning in terms of generating random materials. It's the same sort of idea that if we have a covariance matrix, then we can generate random samples that have that expected covariance, if you take enough of them, by taking your covariance matrix and computing its eigenvectors and eigenvalues. And then as a random slip, you can take whatever your mean is over each of the subfaults, plus a combination of the eigenvectors, a linear combination of the eigenvectors that are weighted by the square root of the eigenvalue comes into it. But then the other factor, the random factor, is z sub k, which is independent random number, normally distributed with mean 0 and variance 1. So the square root of the eigenvalue coming in here gives it the right sort of variance, and using the eigenvectors gives you the right covariance when you look at the expected value of slip on two different subpatches. So this is a powerful way to generate random fields that have a desired covariance structure. And of course, if the covariance length is very long, if the covariance matrix, if you have sort of slow decay of the covariance, then these eigenvalues decay very rapidly, and you can also use this to dimension reduction. You may only need a few terms in this series, even if you have 180 subfaults. For our purposes, we're just kind of doing random Monte Carlo sampling, so that wasn't necessarily an issue, but for other applications, you might want to do dimension reduction as well. So this is just the math of why it is that it works. If we take this formula to generate our random samples, if you just write that in matrix vector form, it's the matrix of eigenvectors times the square root of the diagonal matrix of eigenvalues. And then if you simply calculate the expected value of S minus mu times S minus mu transpose, that's the covariance matrix. And the only thing that's random in here is the Z, and the expected value of ZZ transpose is the identity matrix, because they're independent, normally distributed with mean 1, and so you end up reconstructing the covariance matrix. So that gives us a way to generate random samples. Oh, what the seismologists often do, and what we've done too, is actually use a log-normal distribution rather than a normal distribution. I won't go through that, but you can do a very similar thing that just has the advantage of forcing all of the slips to have the same sign, so we don't have non-physical slip in the wrong direction at some points on the subfault. Of course, if your fault is really just rectangular, like the one I showed you off the coast of Chile, then this KL expansion sort of reduces to Fourier series, that the eigenvectors are just discrete versions of Fourier modes, and then how you sort of put in the decay is related to what the seismologists call the power spectral density of the fault, and there's been a lot of work sort of using this kind of approach in the past in the seismic literature. But looking at it more generally as this KL expansion allows you to handle faults that look more like this, the Cascadia subduction zone, where it isn't a single rectangle. Here it's this particular representation we used here was a union of rectangles, but you can also do the triangulation, which I'll show you later. And then you can do the same sort of idea looking at the covariance matrix that you want on this union of subfaults, and then look at the eigenvectors of that. And if you sort of plot those, what they end up looking like is Fourier modes, but better on this more complicated geometry of your actual fault. So this has proved to be a useful way to generate random earthquakes. We started looking at this some years ago, but Diego picked up this idea and started doing some work on it with people at Berkeley when he was a postdoc there. And then in these papers, we were mostly looking at sort of the methodology of using this without necessarily having the right values for the correlation length on these faults, but in some very recent work of Diego and Gavin Hayes at the USGS, they've looked at a lot of the data from other megathrust earthquake events and come up with better guidelines on what the right correlation lengths are to use for this kind of expansion. And so here are some of the realizations that Diego and Amy came up with for this most recent work. And again, we had 4 different classes, 7.5, 8, 8.5, and 9, and this is just showing one from each of those classes. We actually used 500 from each class in our modeling, and these were actually generated on a more realistic model of the Cascadia subduction zone that is based on triangulation. So this shows 2 random magnitude 9 events. One, this number 1665, happened to be centered down around Crescent City, which is another location that we looked at. Realization 1999 was centered more in the north around Westport, which is the one I will focus on here. So again, this is what Westport looks like. There's another shot of that. So this 1665, the one that gave a relatively small tsunami around Westport, most of the peninsula stayed dry. That's what the green is here. The blues are where the flooding depth was 1 or 2 meters. This other event, 1999, gave much deeper flooding across the peninsula, where the reds are now more than 2 meters, going up to above 10 meters in some places. And what's shown here is that 1665 realization, again, as computed on a fine grid on the left here, which is what we would like to do for all of these realizations, is compute on a very fine grid. But if you're doing a couple thousand of them and looking ultimately at lots of different places along the coast, you can't afford to do it on a very fine grid everywhere. So for this study, we also looked at what happens if we solve it on a much coarser grid, coarser by a factor of 15 in each direction, which requires a lot less computing time, but doesn't give you the same sort of resolution. So that's what's shown in the top middle here compared to the fine grid simulation. So it captures some of the right flavor, but not any of the details. So then we've looked at a couple of ways to improve those coarse grid simulation results without doing a fine grid simulation to get something that's closer to the fine grid with a lot less work. So I'll talk about a couple of these. One is what we call the Coarse-mod correction, where we've combined the flooding level from the coarse grid with the finer grid topography, and we get a finer scale representation of the flooding. I'll illustrate that a bit better on the next slide. And then a more sophisticated approach where that's also combined with the results of other simulations to create what's called the pseudo-fine simulation. That's a much better representation of the fine grid simulation without doing all of the work of the fine grid simulation. So in this case, in the right column is the same in all 3 cases. It's just the fine grid simulation, but now this is a better representation of that, and these are the differences. And similarly for this bigger event, where you can see the coarse grid doesn't have any of the details about areas that stayed relatively dry, where these ridges are on the peninsula, whereas by the time we've done these corrections, you're picking up much more fine scale information, even though this is still based entirely on the coarse grid, or almost entirely on this coarse grid simulation. So this Coarse-mod correction is based on the fact that when you look at these simulations, this is the maximum flooding depth on some transect cutting through Westport, the one I showed before. The maximum flooding depth or the maximum flooding elevation tends to be relatively constant, even though the topography below it is varying. This long wavelength wave comes in and kind of fills in all the way to this first ridge, and then it flows over there and fills in this valley and so on. And so even though the depth of water is varying quite a bit, the surface is fairly flat and can be represented well on a coarse grid, and is actually calculated reasonably well on a coarse grid. And then by looking at the depth by taking that elevation minus the actual finer grid topography, you get a much better representation of what the depth is on the fine grid without doing fine grid calculation. The other correction we do is also based on the fact that when we run lots of different simulations, we find that even though there's quite a bit of variation, you often find very similar inundation patterns from different events. They flood this similar area even if the earthquake was quite different. And so rather than having to do thousands of fine grid simulations, we found that we can do a much smaller set of fine grid simulations if we first cluster based on the coarse grid simulations into clusters that we think have similar behavior, and then do only one fine grid run for each cluster, what we call the cluster representative. So in the examples I'll show, even though we had 2,000 realizations overall from these 4 different classes, we clustered them into only 18 clusters and then did only one fine grid simulation from each cluster. And we can use those to either assign a weight to the entire cluster, say assume everything in this cluster is going to flood in exactly the same way. And so we'll only do that one fine grid simulation and then assign a weight that's the sum of all the weights corresponding to events in that cluster. Or you can do something more like a multi-resolution Monte Carlo idea, where we do the coarse grid simulations of all of the other ones in the cluster, but correct each of those based on the difference between the fine grid and the coarse grid simulations for the representative for which we have both fine and coarse grid simulations. And it turns out that correction also works well to sort of correct the coarse grid simulations from the other ones in the cluster and give a better approximation to the fine grid solution. So I went through that quickly, but the idea is that we can, instead of doing 2,000 very fine grid simulations, we can do at most, say, 18 fine grid simulations, perhaps with many more coarse grid simulations, and then cluster them somehow by looking at various quantities from the coarse grid simulation. In this particular work, we looked at 3 different quantities that sort of measured how big the tsunami was in different ways around the community we're interested in. And so then we had a 3-dimensional space, and each one of the 2,000 coarse grid simulations gave us a point in this 3-dimensional space. And when you plot all those points, you find that they tend to kind of lie on these lower dimensional structures. And so you can do a k-means clustering to cluster them into groups of events. And then the big X's are the representative from each cluster that was chosen for doing a fine grid simulation. And all of the other events, we only did the coarse grid simulations. So once you've done that for all of these different events and combined them all, then as I said, you can calculate these hazard curves. So this is that one particular point where the red point is here in Westport, but you would have to do this at every point over the community. And so at this particular point, after doing these 2,000 coarse grid runs and then 18 fine grid runs and then combining all that information, we can get the hazard curve that shows for different exceedance values for different maximum flooding depths, what is the annual probability as estimated by the fraction of events that exceeded that, weighted properly by the probabilities of those events. And there's 2 curves here. The blue one is the curve we got by actually solving all 2,000 fine grid runs that we did for this particular community as our baseline, our ground truth that we were comparing against. So that we're assuming is the correct hazard curve based on our assumption about the probability distributions. And then the orange curve is what we got by using this pseudo-fine approach where we only used 18 of those fine grid simulations together with the coarse grid simulations. And what you see is they agree quite well until you get to these very large events. This is on the outer coast here on the Pacific coast. So there were a few events that actually gave 15 meters of flooding or more than 10 meters of flooding, but there were relatively few. So those probabilities are not very well estimated by this approach, but we're getting down here to probabilities of 1 over 10,000 year sort of probabilities. If we go back up to the more reasonable probabilities that we care about, like the 4 times 10 to the minus 4 is the 2,500 year event. At this level, the 2 approaches are pretty much agreeing very well, certainly within the uncertainty of everything else we're doing, and would tell us that at this particular point, we would expect the 2,500-year event to give us about maybe 7 or 8 meters of flooding. And then again, you have to do this at every point in the community. Here's a different point that's close to where they're hoping to build another vertical evacuation structure in Westport, close to the harbor. The water sort of has to come around through the harbor here, so the exceedance values are the maximum flooding depth is smaller here, but you see a similar pattern. Again, the low probability events don't get captured very well with this approximation, but up in here, where we care about, we're getting a very good approximation with a lot less computation. So then, once you've done this at every point in the community, you can combine all of those, or you've done it on a fine grid covering the community, you can combine all of those and get a probabilistic map. So what's shown up here is for a particular return time, 500 years. So looking at 0.002 for each of these plots. And so for this one, for example, there's no flooding with the 500-year 0.002 probability at this point on the coast. There is some flooding at that probability. You would combine all of those together and you would get this sort of map that would say there's a little bit of flooding around the coast in the 500-year time frame. And this is, again, the one that was computed using all of the fine grid simulations. These are a couple of other approximations, but the one in the bottom right is the one using this pseudo-fine approach that we hope approximates it fairly well. If you go to a lower probability, you of course have more flooding. So the 2,500 year, 1/2,500 annual probability, then you see flooding of most of the peninsula, except for these ridges. Again, these ridges aren't even represented on the coarse grid, and yet when you do the Coarse-mod correction alone, you're already getting some of that structure showing up. And with the pseudo-fine approximations, we're getting a probabilistic map here that looks pretty good. So that's the goal. It's a little hard to just compare these plan view plots for different probabilities. So we've also looked at transects cutting across the peninsula. So this is a transect cutting through the middle of the peninsula here. And now what we're showing is, together with this, of course, vertically exaggerated scale of the topography in green, we're showing the expected flooding depth with 4 different annual probabilities. So the cyan curve, the lowest one is 500 year, 1,000, 2,500, and 5,000. And in this case, the dashed line is what would be obtained using all of the fine grid simulations. So that's our ground truth. And the solid lines are what we compute with these coarser approximations, much more cheaply. And so going forward, where we want to be able to do this kind of thing for many different locations along the coast, potentially for all 3,000 miles of the Washington coast eventually, it becomes very important to be able to do this efficiently. And so we're continuing to push forward on improving the methodology. We're also continuing to work with the seismologists on better nailing down what's the right probability distribution to be putting into this methodology. So again, there's a number of papers, and in many cases, the code that goes along with them on our web pages. If you just go to geoclaw.org, you can find links to many of these things. So I'll stop there, except I would like to take a couple more minutes and just mention one other issue. As you may recall, there's an election coming up in a couple of weeks. And so today has been a nice break from thinking about that, but I do hope that everyone who's in the US and is eligible to vote is registered and will do so. And vote.org has a nice website that allows you to figure out how to register in any state in the union and to check on your registration. So I encourage you to go there. But also, if you're, for faculty in the audience, I really encourage you to also urge your students to make sure they're registered and that they vote. And many universities are now encouraging this and have big get out the vote efforts. The University of Washington, for example, at this website. And so I think it's fine for faculty to encourage students to register and vote. Of course, you have to do it in a nonpartisan manner, so check with your own university for any regulations. But I encourage you to look into what's being done at your university and reach out to your students if you can. So I will stop there.
All right, thank you. Are there questions for Randy?